Hi everyone. So this lesson is about AC in a pure inductor. So you've got to learn about what happens if there's just a resistor in an AC circuit, what happens when there's just a capacitor in an AC circuit, and then we learned about what happens when there's a resistor and a capacitor in an AC circuit, and this is the last part, nearly, when you have just an inductor in an AC circuit. So let's just try and recall what an inductor is. So inductors are coils of wires, and when there's a changing current in that inductor, through that inductor, there's also going to be a changing flux, because whenever you have a current through a wire, you have around it flux or magnetic field. And whenever there is changing flux, what happens is there's going to be an induced voltage that's going to oppose this change, that's going to prevent the current from changing. So what we have learned is what happens when there's an inductor in a DC circuit. And in a DC circuit, an inductor only acts like an inductor when the current is changing. And there's only two instances in a DC circuit when the current is changing, and that is at switch on. So when you close the switch and the current goes from 0 to a maximum, or when you disconnect the battery and the inductor is just discharging, or at switch off, when the current goes from maximum to 0, because those are the only two times the current changes and therefore changing flux. And we just have to remember what the induced EMF, it's also called as induced voltage, it's also called back EMF, they're all the same thing, and it depends, and what it does is to prevent the change. Okay, once the current is steady in a DC circuit, the inductor stops having any voltage across it, and it's only the resistor that's going to have a voltage across it. Okay, because when there's no change in current or flux, there is no back EMF or opposing voltage. However, in an AC circuit where the current is always changing because it's going back and forth, there will always be an induced voltage across the inductor. So an inductor is effective the whole time in an AC circuit. So that's the difference between the inductor in an AC and a DC circuit. Now, just like we did for capacitors, if we're going to use Ohm's law for inductors, and that is what is the connection between the voltage across an inductor and the current through the circuit. So if we have a similar sort of setup for the inductor, so if you have your AC circuit, you've got an ammeter to measure the size of the current, you've got your inductor, that's your L, and then a variable resistor or a rheostat to change the current. And what are we trying to do? So we are trying to measure the voltage across the inductor, and if we draw a graph of voltage against current, but this time it is the voltage across the inductor, this one here, and the circuit current. So just quickly get all the units. So current is measured in amps, voltage in volts. You're going to get a straight line through the origin, which tells us that the voltage across the inductor is directly proportional to the circuit current. The constant of proportionality in this case is reactance, just like we had for the capacitors, but the difference will be put IXL, L for the inductor reactance. So the inductor reactance is also measured in ohms, and it is the current limiting property of the inductor. Okay, now just like we did for the capacitors, let's look at the factors, or what is it that affects the reactance of an inductor. So factors affecting XL, which is the reactance of an inductor. Two things, one of them is the frequency and the other is the inductance itself. So it's the frequency of the supply, so frequency is F, and the other thing is inductance, which is L. So again, what we have to keep in mind is when the reactance is large, because it's a current limiting property, the current is going to be small. Okay, so let's look at, if the frequency increases, that means the current is changing more rapidly. So the greater the rate of change of current, greater the rate of change of flux, so larger the induced voltage, which is opposing the change, and so the current is going to be low, or so that means the reactance is going to be high. So the inductance of the reactance of an inductor is actually directly proportional to the frequency. Okay, so when frequency increases, reactance is also going to increase. And then the other thing is the inductance itself, L. So the inductance of an inductor is directly proportional to its induced voltage. So that means, again, the current is going to be smaller. If the inductance increases, that means your reactance is going to be higher. So the formula for the reactance of an inductor is that the reactance of the inductor is directly proportional to both the frequency and the inductance. The constant of proportionality is 2 pi. So the whole equation becomes XL is equal to 2 pi FL. The way that this is given in your formula sheet is that XL is omega L, where omega is equal to 2 pi f, and omega is called angular frequency, or it's okay. So that's what this looks like. So I hope that made sense. And the only thing that we have to remember is that that angular frequency is measured in radians per second, and your reactance is measured in ohms. Okay, so I hope that made sense, and bye for now.